Okay, so now we're finally going to put all this information together and understand how explosive volcanic eruptions occur. And we'll start by talking about processes in the conduit as magma rises up from a magma chamber towards the surface. And then later on, we'll get to what happens up here when the ash and gas exits the vent of the volcano. So it's all in the bubbles. Explosive eruptions is really all about bubbles. And we learned that there are volatile constituents, such as water and carbon dioxide, that at high pressure are dissolved within the magma. But as the magma rises, the pressure decreases, and at some point, depending on the composition of the magma, how much water, how much CO2 is dissolved, we reach the solubility threshold, and a separate gas phase would thermodynamically be favored to form. In other words, we go into the part of the phase diagram where we have liquid magma plus separate gas phase. Depending on how rapidly the magma is moving, the bubbles may not form immediately. Just because they're energetically favored to do so doesn't mean that they happen instantly. So there's actually a competition between forming a bubble would decrease the energy of the system, and that change in energy will go with the volume of the bubble. That goes like the radius of the bubble cubed. That's here. But it takes energy to form the wall of the bubble, the interface between the gas and the liquid. And that change in energy scales with the surface area, or the radius squared. So when you put all that together, what happens is that bubbles form at a critical dimension with a radius r critical. So nucleation of bubbles is actually promoted by impurities in magmas. Those impurities could be things like crystals. Actually, if you look at a glass of beer, for example, and look carefully at where the bubbles are forming, you'll find that most often they're coming from the edge of the wall of the container, the glass. And in particular, if you really look carefully, you'd see that there are little scratches and imperfections on the surface of the glass, and those imperfections are helping the bubbles to nucleate. And so it is the presence of impurities, such as the scratch on the glass or the presence of crystals, that help the bubbles to nucleate. So we actually call that heterogeneous nucleation when there are when there are impurities, and that aids the formation of the bubbles. When there are no impurities, you get what's called, I shouldn't scratch that out, you get homogeneous nucleation. And in homogeneous nucleation, the formation of the bubbles can actually be delayed somewhat, which leads to supersaturation in the volatile phase. In any event, sooner or later, the bubbles will form, and then there are a variety of processes which act to either make the bubbles grow, to increase in size, or resist the bubbles expanding. The processes that promote the growth of the bubbles, the first, is the diffusion of the volatile species into the bubble. So once a bubble forms, water molecules that are dissolved in the melt are going to diffuse towards the bubble wall and then enter the bubble, because that's where they're thermodynamically favored. So as more water or CO2 diffuses into the bubbles, that will make them bigger. Another important effect is just the mechanical expansion of the bubbles. That as the pressure decreases, the volume of the bubble will expand. You all remember the ideal gas law: pressure times volume equals at constant temperature a constant, or PV equals nRT. So that means that the velocity and the pressure are inversely proportional to one another. So again, as the bubbles, if you look in the glass of beer, you'll see as the bubbles come up, the pressure goes down, the volume of the bubbles will expand. So those are things that are acting to make the bubbles grow in size. The growth of the bubbles is resisted by the viscosity of the liquid. In order for the bubble to expand, the liquid has to move out of the way. And for very, very viscous lavas or magmas like rhyolite, it's hard for the bubbles to expand against the high viscosity of the fluid. And the last factor here is coalescence. Bubbles can actually bump into one another and then coalesce. So here we have in this figure on the right-hand side over here, we have bubbles of different sizes. We have large bubbles and small bubbles. And there's a relatively simple formula called the Stokes velocity that tells us how fast the bubbles will rise relative to the fluid. So this velocity of the bubbles is relative to the magma. So if we imagine the magma being not moving at all, then this would just be the rise of the bubbles. So the velocity that the bubbles will rise depends on the density contrast, how much less dense the gas is relative to the liquid. So the bigger the density contrast, the faster they'll rise. G is the gravitational acceleration. Eta is the viscosity of the fluid, so that's in the denominator. The higher the viscosity, the slower the bubbles will rise, the harder the time they have rising up through the fluid. And interestingly, the velocity depends on the diameter of the bubble squared. So big bubbles rise more quickly. So you can see the arrow here on this guy is much larger. The big bubble is rising rapidly, the small ones are rising more slowly. Okay, and as I was saying, because the larger bubbles are moving faster than the small ones, the big ones can sweep up the small ones, and that's another mechanism for the bubbles to expand. So let's think about now what's happening. If we call v the velocity of ascent, oops, let's clear that. If we call v the velocity of ascent of the melt, and v sub b is the bubble velocity, then if the magma is very, very viscous, then the bubbles have a hard time flowing through the magma. And what happens is then, in that case, they get transported with the magma. They're just carried along. And that's what's going to happen in our very viscous magmas that lead to explosive eruptions. On the other hand, if the magma is moving very, very slowly, and you have a low viscosity magma, this could happen in a basaltic magma system like Hawaii, where there can exist lava lakes. These lava lakes are essentially stationary pools of liquid rock. Then the bubbles can rise up through them and actually coalesce, turn into larger bubbles, and then burst at the surface. It's already mentioned that the large ones can sweep up the smaller ones. And we think that's at least the most commonly accepted model of strombolian eruptions, that these bubbles coalesce together and they form what are called slugs. That's illustrated in this cartoon here. Instead of having dispersed bubbles of small size, the larger ones sweep up the small ones, collect into relatively large pockets or slugs of magma. When they reach the surface, they burst, and when they burst, they send clots of molten magma shooting up into the sky. And stromboli, for which strombolian eruptions are named, typically erupts every 15 minutes or so and just sprays liquid rock into the air. It's a very spectacular volcano. Okay, so now we understand something about how bubbles nucleate as the gas phase, water, CO2, other volatile constituents, separate and form a separate gas phase in small bubbles, and those bubbles will expand as the magma moves up towards the surface and the pressure decreases. So we see that in cartoon form here. Imagine this magma is moving up towards the surface. We start with very low concentration of small bubbles. As it moves up, the bubbles get bigger, the pressure is decreasing, they're mechanically expanding, more constituents are diffusing into the bubbles. And at some point, about here, you get what you'd actually call a foam. This looks like the foam on a carbonated drink or beer, where it's mostly bubbles with just a little bit of liquid surrounding the bubbles or sitting in the interstices between the bubbles. And then finally, when the bubble concentration reaches a critical value, which is something like 70% bubbles, then the bubble walls start to break. And we call that fragmentation. So right here, at this level, we have fragmentation. The walls of liquid silicate rock between the bubbles actually fragment, and when all that is done, we now have, as in this diagram here, instead of a bubbly liquid, we have what people refer to as a dusty gas. We have a gas, predominantly gas, with particles floating around in the gas that were actually made up of what used to be the walls of the bubbles. This diagram over on the left-hand side is showing pressure on a logarithmic scale going from high pressure to low pressure that way. And on this axis is the volume fraction of gas from 0% all the way up to 100%. We show that for two different concentrations of water in the magma. So let's look at 1.84%. As the pressure decreases, at this pressure here, we reach the solubility, so a separate gas phase forms. It's now a very, very tiny amount of the magma, but as the pressure decreases, we go down, the volume fraction, percent of the magma that's made of gas, goes up to 80%, 90%, and eventually it's almost 100% of the gas. Sorry, 100% of the magma is composed of gas. Okay. If we were to look at the lower concentration, we would wait till a lower pressure before the bubbles formed. We reach the solubility point. Gas is now favored. We get nucleation of bubbles. As the pressure decreases, again, the volume fraction of gas goes from very small values to essentially 100%. So this is real. I mean, this is really what happens, and we can see that by looking at scanning electron micrographs of different kinds of pyroclasts. Remember, pyroclast, pyro is hot, and clast means fragmentary. So these are basically little pieces of volcanic rock that's been ejected into the atmosphere. And you can see the shapes of the bubbles. This is a very special kind of rock. I'll bring in a sample. This is called reticulite, and you can see that it's almost like a lattice work of silicate melt. This is glass. It was at one point molten rock, and the dark area are the bubbles. So this is a very low density foam. You can see it's 98% vesicles, or the word that geologists use for the bubbles. So it's 98% bubbles. It's only 2% glass. Here's some from Mount St. Helens down here, and you can see where these bubble walls are beginning to fragment. And when they fragment, they leave little pieces of leftover material, which is what volcanic ash is. Volcanic ash is just these little fragments here. We can see it up in this one from Crater Lake where it's fragmenting. So there's a little piece of ash that used to be attached in this foam network, but is now broken apart. Okay, so this is what this process looks like after the fact when we see it in a magma.